Hi and welcome back to the series of questions from the Leaving Cert 2008 Higher Maths Paper 1. Now, today we're looking at question 5. Okay, part A, find the range of values of x that satisfy that inequality, x squared minus 3x minus 10, all less than or equal to 0. It's a good idea to imagine the shape that this equation leads to. Okay, there we have the graph of a typical quadratic, not necessarily this one. In other words, what we have is a parabola that dips below f of x equal to 0 or y equal to 0 at some point and comes up again at another point. This question asks us for that range of values, the shaded part of the diagram, where the curve takes on negative values. So, by finding out the crossing points where f of x equals 0 and choosing the range of values in between, we have the answer. This amounts to setting the equation to 0 and solving it in the common way. You can invoke the standard equation here, but by knowing that the addition of the two solutions equals the coefficient of x, in this case minus 3, and their multiplication equals the final constant number, minus 10 in this case, visual inspection of the equation is enough. The answer is clearly and neatly that x is greater than or equal to minus 2, or less than or equal to 5. This can be checked by expanding x plus 2 by x minus 5 and seeing the given equation come out. On to part B, section 1. Solve the equation 2 to the power of x squared equals 8 all to the power of 2x plus 9. The power of a power in this question makes it look complicated, but logarithms can come to our rescue, especially if we choose log 2. It is very necessary to know the rules of how logarithms operate, and by converting multiplication to addition, a fact that helped a lot in life before calculators actually. What happens is as follows. We take our equation, and it implies, by taking logarithms on either side, we can take down the powers in either case and multiply them by the log. Okay, now log 2 of 2 actually is 1, and log 2 of 8 is actually 3. A quadratic equation then results, pretty much like, but not exactly the same, as part A of this question. In other words, we get, by bringing the left-hand terms over to the right-hand side, x squared minus 6x minus 27 equals 0. Where analysis of the coefficients once again tells us that the solution must be neat and easy, as in x equals minus 3 and plus 9. Once again, for verification, we can expand x minus 9 multiplied by x plus 3 to make sure we have the right answer. Okay, on to section 2 of part B. Solve the equation. This time, it's a logarithmic equation rather than an exponent equation. The answer The second section of part B involves carrying out the operation which reverses the logarithm. This happens to be the exponent e, and we can carry it out as follows. There we have our equation, and we take the exponent e of either side. So we bring all the terms to the power of e on either side. Now the addition in the power of the exponent can actually be split and turned into a multiplication. Okay, so we see that happening on the right-hand side. The left-hand side we don't change. Now, to take the exponent of a logarithm essentially cancels the operation out. Okay, so we take the 2x plus 3 and multiply it by the x minus 2, and that all equals x plus 4 squared. Okay, so the equation has not changed. We've merely used the rules of exponents and logarithms. Again, it shouldn't be a mystery what we've just done if one observes the rules of exponents properly. By expanding, we can predict that a quadratic will result, which, with any luck, will have just as easy and neat a solution as the other quadratics seen previously in this question. Okay, so it's a matter of merely manipulating both sides and getting the quadratic, which is x squared minus 9x minus 22. Again, we rely on visual inspection and consideration of coefficients to guess that x equals minus 2 and x equals plus 11, which once again we can verify for the third time in this question by expanding x minus 2 multiplied by x plus 11. Okay, so we move on to part C, which is a geometric series question. Show that there are no natural numbers n and r for which that expression are consecutive terms in a geometric sequence. Okay, by no natural numbers n and r, we take to mean that if we treat the sequence as a geometric one, and if one of either n or r happens to be either a negative number or a fraction, then we will have shown that both together cannot be natural numbers. I will reread that because its exact meaning is fairly crucial. By no natural numbers n and r, we take to mean that if we treat the sequence as a geometric one, and if one of either n or r happens to be either a negative number or a fraction, then we will have shown that both together cannot be natural numbers. We also met geometric sequences in question 4, and we know that dividing the second term by the first and the third term by the second, we should get the same answer. In other words, we divide the second term by the first and let it equal the third term divided by the second. This notation should be recognized as the choose R objects from a set of n, as used in the area of combinations. Basically, it is a notation for factorials, which we can represent as follows. Note that we invert the divisor in this equation so that we can actually multiply. So that expression on the left should come as no surprise, because that is what the notation represents. And on the right hand side, by the same argument, that notation once again is represented by that fraction. Remembering that factorials are multiplications of the number as it descends to 1, we take note of a number of cancellations that can take place, the most obvious one being the n factorials on either side. So what we get is n minus r plus 1, no factorials this time, all over r, by n minus r all over n plus 1. The factorials have disappeared, okay? That has to be checked via the cancellations that come naturally from factorials. Okay, multiplying across by the two denominators, we have to carry out some manipulation of that equation, but it's all totally legal. Several cancellations occur, and we end up actually with n equals minus 1, which is not a natural number. We do not need to go and find r at all, because we only needed that one of either n or r to be a non-natural number. It's nice to do some verification though, if time permits, and we can set n equal to 5 and r equal to 3, and we get the sequence 20, 20, 15. Doesn't look like a geometric sequence, does it? And also set n equal to 7 and r equal to 4. Okay, try it again, whereupon we get the sequence 35, 35, 21. So, though not exhaustive by any means, the verifications are reassuring. No natural number geometric sequences can result, and our answer is now complete. Thank you.